Another Leetcode problem. 1438, longest contiguous subarray with absolute diff less than or equal to limit. So the meaning is that we are giving an array nums and we want to find the longest contiguous subarray. So for example, 8 is maybe the longest, yeah, and 2, 4 may be bigger than 8 because 2 and 4, the length of them is 2, and 4 minus 2, the absolute value of 2 minus 4 or 4 minus 2, it is a 2. It is a less than limit, so it is okay. So the length is going to be 2. So let's have 4 and 7. It is also okay. But what about the 2 for 7? It is not okay because 7 minus 2, it is 5. Or maybe 8 to 4, it is that okay? Because 8 minus 2 has already been more than the limit. So it can never be 8 to 4. 8 to 2 is not okay. Yeah. So in this example, we're going to return a 2. So actually what we are doing, we are going to check the longest distance and for any of the numbers. So for any of the numbers, the absolute difference is going to be less than and equal to limit. Yeah. So if we can, so the obvious idea is that we can use the sorted list. Because in Python, the sorted list is a balanced binary search tree. So for each of the numbers, so for example, for example, we have a number 8, and we have a number 2. 2 is smaller, and this 4 is bigger than 2. It's gonna be here. This is a balanced binary search tree. Yeah, and for that 7, it's gonna still go to the left side. Yeah. So if it is balanced, so this is gonna be 8, and here gonna be 7. Yeah. So if it were to keep, if we can keep it a balanced binary search tree, maybe we're gonna totally change the structure. Yeah. Maybe it's gonna be like 7. And this side it is 8, 4, and from this side it is 2. As you can see, this is a balanced binary search tree. So if we can use a sorted list, basically we can solve it by using n log n time. So this is because we can keep a range. So for example, we keep a range of 8 to 2. It is not okay because inside a sorted list, so the numbers will be sorted like 2 and 8. So 8 minus 2, from the last number minus the first number, it is more than 4. It is not okay. Then we can use the sliding window to shift it. Yeah. Now we're gonna pop out this 8 and check 2 and 4. So 2 and 4, 4 minus 2, it is less than the limit. So we're gonna record the result. It's gonna be 2. And what are we gonna do next? Next, we're gonna check the next number. Yeah. So if the next number is 7, 7 minus 2 is more than 4. So we're gonna pop it out and we're gonna check again, and the result is gonna be 2. So this is a sorted list solution, and it's gonna be n log n time. So the sorted list basically it is a balanced binary search tree, because if we put it as a balanced binary search tree or a sorted list, yes, but for sorted list we can check the first number and the last number just in O1 time, and we can add an element or remove an element in log n time. Yeah. So this is similar like a balanced binary search tree. But for our problem, I'm gonna use the monotonic stack to solve it, a monotonic queue to solve it. Because in monotonic queue, we can prepare 2 queues. So one is monotonic decreasing queue, another is monotonic increasing queue. So for the first element, maybe this is 8, as this is monotonic decreasing queue, and this is monotonic increasing queue. Because of the first element is 8, and then 2 is less than 8, so we're gonna pop out this 8 and put 2 here. So this is number 2. And then we're gonna compare with the first element in the monotonic decreasing queue with the first element in the monotonic increasing queue. So if this 8 minus 2, the first element 8 minus 2 is more than the limit. So we're gonna try to pop it out. But whether we're gonna pop out 2 or 8, it is dependent on the positions. So we're gonna prepare a pointer L. This is starting from 0. This is gonna be the positions. If my nums L equals to 8 equals to my current number, so for example monotonic decreasing Q equals to this 8. So what I gonna do? I gonna pop left. I gonna pop this 8 out, and the next number may be 2. So 2 and 2, it is okay. So I have a distance of 1 currently. Yeah, and then I gonna check next. So for the next, I'm gonna put 4 inside. If it is monotonic decreasing Q, I'm gonna pop 2 out, and this gonna be 4. And as this is monotonic increasing, so I'm gonna put the next number. So it is 2, 4, and 4. So for 2, 4, and 4, 4 minus 2, it is a less than limit. So it is okay. And then I'm gonna check the next element. Yeah, if this is 4 minus 2, and then I'm gonna check the first element. So the first element is 2. So I'm gonna pop 2 out and put 4 here. So currently this is 4. Yeah, currently I don't have 2, and for my monotonic increasing Q, I only have a 4. Yeah, now this is 4, this is 4, so it is a less than limit. 4 minus 4, 0, less than limit. And then I'm gonna check the distance. Yeah, so for this 4, and did I do something wrong? Let me just yeah, no, I think I didn't, because here is 2. I've already recorded the distance. It is okay. Currently the distance is 2, and then I put 4 here, so the distance is gonna become 1, but the maximum distance is gonna be 2. Yeah, so this is the monotonic Q idea. Basically, one is decreasing and one is increasing, and this Q can never be like that. I mean, this top value minus this value must be also monotonic, otherwise we cannot solve it. I mean, it can never have this kind of operation. Yeah, it can never come to here. It is not monotonic. Yeah, so basically the structure of a monotonic decreasing and increasing Q would be like this, or it would be like this, or it would be like this, but definitely it can never be like that, because that is not monotonic. I mean, this value x minus y should always be monotonic decreasing. It's gonna be smaller and smaller, as you can see that it is. Yeah. Now let's try to use monotonic Q to solve it. So we're gonna prepare a result and L pointer, left pointer, and we're gonna prepare decreasing Q and monotonic increasing Q. Yeah, we're gonna basically need to prepare 4 variables. This is our result. L is the left pointer, also starting from 0, and increasing Q and decreasing Q gonna be a double-added Q. Yeah. Now we can prepare the monotonic Q structure. So for I, X in enumerate the nums. So first of all, let's prepare the monotonic decreasing Q. So while decreasing Q and current value X is more than nums. So here it is basically a monotonic stack data structure up to here. Yeah, so it's gonna be the decreasing Q minus 1. Yeah, first of all, we're gonna pop it out if it is more than that. Otherwise, we're gonna put it inside. Yeah, so we're gonna pop it out. So decreasing Q should pop. We're gonna pop out from the right side, and then if it is okay, we're gonna put it inside. So the decreasing Q gonna append this I gonna use the index. So every index I'm gonna put it inside the decreasing Q, and also I want to put it inside the increasing Q. So I just need to copy and paste, and here I'm gonna change it to increasing Q, and here also be increasing Q. As it is increasing Q, the X should be less than nums increasing Q minus 1. So here, similarly, just increasing Q pop and increasing Q append. Yeah. Now I basically prepared 2 monotonic Q. So one is the decreasing Q, another is increasing Q, and I put all the index inside. Now I want to check the limit. So while, because the decreasing Q or top the element might be more than or equal to the increasing Q, I mean on top of that element, so this decreasing Q 0 minus increasing q 0 while they are less than the limit. So I would choose pop it from the left side. So the decreasing q gonna pop left, and increasing q also gonna pop left. Yeah, but I'm not sure what I need to pop it, so I gonna have an if tag. So if my current index L, yeah, so if decreasing q 0 on top of the index equal to my current index L, so I'm gonna pop out the decreasing q from the left side. So if increasing q 0 on top of that element equal to the index L, so I'm gonna pop the increasing q from the left side. Yeah. So this if tag has three different cases. One is I only execute this one. Another is only execute increasing q. And the third case is that I'm gonna execute both sides. Yeah, because maybe this is 8, increasing q, decreasing q, it's the same element, maybe 8 and 8. Or maybe it is like this. Yeah, I'm gonna check one of the elements. If everything's okay, up to here, I can record the result, and it's gonna be the result with I minus L, my current index, at the left side plus 1. Yeah. Now I can out. As you can see, everything inside, this is monotonic decreasing q, and this is monotonic increasing q. Yeah, because we are checking a window, the maximum window, and from here, this is basically a sliding window structure, and this is a monotonic stack structure. So we're gonna plus them together, and we're gonna make a monotonic Q structure. So it is a monotonic decreasing Q and increasing Q together, because for our problem we have to put it together to solve it. Now let me run it to check. Yeah, there's something wrong. Yeah, let me just check what is wrong with it. Yeah, because this is the index, I need to use the numbers. So it's gonna be nums with this index and another nums with the index. Yeah, and here this is comparing the index. It should be okay. Now let me run it. Yeah, I think there's gonna still be some problem because we didn't update the left pointer, because this is basically a sliding window. If we didn't update the left pointer, we're gonna have time limit exceeded. Yeah, so it is a time limit exceeded. We have to update the left pointer. So L should plus equal to 1. So this means so for 2 of 8. So if this one meets the condition, this one meets the condition. Yeah. So if this one more than the limit, so we're gonna shift to this one and this one. If it is okay, we're gonna stop the while loop. But if we didn't update the L pointer, we can never stop the while loop. Yeah, so this means if we go inside, we have to stop it, and we have to check where it is and the position. So we have to update the L pointer because we popped out the element, for example 8, we popped out, and yeah, we're gonna update the pointer to check the next element. It is 2, so maybe the next element is 4. We have to update the pointer. Yeah. Now let me run it to check. As you can see, now works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it passed all testing cases, and it's pretty fast because we are using the monotonic Q to solve the problem.